So I'm going to talk a little bit about the history of climate modeling and specifically global climate models and global climate change scenarios. And I would introduce the stress and RCP policy scenarios from the IPCC. As I said, there is somewhat misunderstanding, at least in the general public, about what is really climate modeling about and what are models in general. And you all understand that the model is just a representation. So, we can talk about paper model, we can talk about scientific model, we can talk about mathematical model, we can talk about conceptual model. Here, I'm going to focus specifically on the climate models, and the climate models are really meant to simulate what is going in the entire climate system, not only in the atmosphere, but also in other parts of the climate system, such as the ocean, such as the ice, such as biosphere, soils, and so on. There is a number of different climate models, and they all have very different levels of complexity, and these include energy balance climate models and radioactive convective models and statistical dynamic models. And some of these models can be very complex. Some of these models can be very simple. For example, fairly simple models are simply looking at the relationship between the temperature and latitude or the temperature and altitude. We are going to talk today about the so-called general circulation models. You have probably heard the term GCM. Many people refer to GCM as global climate models, but those are actually general circulation models, and they simulate what is happening in the climate system, what kind of changes we might expect in the atmosphere and in the ocean, and especially in this whole interaction of climate system, including both ocean and the atmosphere, as a result of higher concentrations of greenhouse gases. And that's why, they're sometimes called AOGCM, atmosphere, ocean, general circulation models. Again, models can be very complicated or they can be very relatively simple. So if we look at the history of climate modeling, that was really starting with 1960s, there are fairly simple one-dimensional models. So radioactive convective atmospheric models, upwelling diffusion models in the ocean. Those are examples of 1D models. There are two-dimensional models that are looking either vertically or horizontally on what is happening in the atmosphere or particular layer, the boundary layer of the atmosphere, kind of close to the surface of our planet, or upper layer of the ocean. The general circulation models are all three-dimensional models. So typically they include both the atmosphere and the ocean, and the models have really evolved over time. They used to do separate representation of the ocean and separate representation of the atmosphere. And today, all those models are pretty complex, and they can handle both the atmosphere and the ocean together. And in addition to this, they kind of plug in more and more realistic representation, for example, of the ice caps and even to some extent their terrestrial biosphere, even if it's still very challenging. So you can think about the GCMs really as many systems of mathematical equations that are describing different processes that are happening in the climate system, and they're focusing on the changes in the Earth radiation budget as it's changing due to both natural processes and due to higher concentrations of greenhouse gases. So GCMs can simulate our climate system for any given period of time. They can be ran into the past when the human impact on the atmosphere obviously was significantly low, or even at those times when there were no human impact, and they can also go into the future. And typically they go into the future just up to the end of the 21st century. So GCMs, or as they're called now AOGCMs, so the atmosphere, ocean, general circulation models, are all three-dimensional models. And you can kind of think of the fourth dimension as time. And they very accurately compute all possible changes in the climate system literally for every given day, and they can calculate changes in the atmospheric parameters and changes in the ocean for every season, for differences between day and night. So it's a they're very, very robust, and they're also coupled with cryospheric. So cryosphere is the sphere of ice. So they can also be coupled with models that specifically focus on kind of interaction between the atmosphere and ocean and ice, and also the biosphere models. For example, they do take into consideration the role of carbon sinks and the way how vegetation and soils are responding to climate change. You can think of the whole representation of reality in those models as many, many little cubes, right? So, think of them as the so-called voxels. Pixel is one square on your computer screen. Here we're talking about voxels, basically these little cubes are representing the discrete elements within our climate system. And these AOGCM are developed by a number of leading climate centers all around the world. So you might sometimes hear, from some, misunderstanding students or parents, listen, all these models are coming from the IPCC. Well, they're not coming from the IPCC. What the IPCC, Intergovernmental Panel on Climate Change, is doing, they are screening the quality of those models. They don't develop those models. The IPCC is really the international body that is regularly reviewing all the peer-reviewed research, including research coming from climate models, and selecting the best models. And essentially, they give them kind of the highest level of endorsement, saying, well, we can say that those models are pretty reliable. The models themselves are developed by different climate centers around the world. So, for example, in the United States, we have a number of climate models. One developed by NASA Goddard Center, the other one is developed by NOAA, another one developed by the National Center for Atmospheric Research. And then, there are Canadian models, there are Chinese models, there are models of different European countries, models developed in Japan, and so on and so forth. The fact that all these models are developed by very different centers, by very different groups, developing using different methodologies, and they're all telling us very comparable, very similar stories, actually tells us a lot about their very good agreement. You can think of them, right now we are seeing more and more of different COVID vaccines developed by different research centers around the world. They all use very different methodologies, but their goal is the same, right? To give us immunization against COVID. So the same with climate models. They're developed by completely different groups using very different methodologies, using very powerful computer technology, but they all have the same purpose. So what is really the purpose of those climate models? They help to estimate what would be the changes in the entire climate systems under different concentrations of greenhouse gases. And sometimes we refer to them as concentrations of CO2. But this is, of course, not only CO2, that includes other greenhouse gases such as methane and CFCs and HFCs and so on, that kind of collectively sometimes referred as carbon emissions. And so the models can help us to see what will be the changes in the air atmosphere, what will be the changes in the sea ice thickness, or what will be the changes in the polar ice caps as a result, what would be seasonal changes, what would be seasonal changes of the heat index, and the heat index is a temperature adjusted for the humidity in various geographic areas. They can also help us to see what would be the changes in the sea level rise, what would be the changes in the thermohaline circulation. So the thermohaline circulation is the system of the ocean currents. It's based on the gradients of temperature and salinity in the ocean. And so the models are really helping scientists to see what is going to happen with the global system of ocean currents under different concentrations of CO2, and models agree, for example, that if we see double concentrations of CO2 compared to the pre-industrial level, we see partial collapse, but then recovery and sort of the new system of those ocean currents if we get that to that point when there is a quadrupled concentration of greenhouse gases. Well, perhaps the entire system is going to collapse. So this is just kind of type of questions that these models help to brainstorm and understand about our future. They're obviously very useful for various applications. They can be coupled with agricultural models and help scientists to see how changes in climate would affect specifically soil moisture or soil temperature, and then how it's going to affect specific agricultural crops. They can be linked to the models that are projecting distribution of vector-borne diseases and produce the scenarios for a specific pathogen or for the specific vector. It's important that we communicate to our students correctly the differences between projections and also forecast and scenarios. So, when we think about weather forecast, right? We're thinking about what is going to happen during the next week. Those are fairly specific projections. When we talk about climate, we are talking about much broader, much more aggregated mean averages of weather conditions. And so a climate projection is usually a statement about how likely something is going to happen, how likely, we are going to see certain climatic conditions over time. A scenario, on the other hand, is not really a projection. It's not a prediction. It's more an representation of an alternative. We might think of different storylines about what is going to happen, what might happen in future under certain projections. And so as scientists develop those projections, I'm going to give two examples. I'm going to talk about a little bit about the stress scenarios versus RCP scenarios. So the stress scenarios were developed almost 20 years ago for the third IPCC report, and they still have been evolving. They're still used in by many scientific groups in different experiments. But the idea of stress scenarios, and stress stands by the special report for emission scenarios. So the stress scenarios were developed in 2000, 2001. And the idea behind that might sound today a little bit outdated is that the world is torn along two axes. The one is contradiction between global priorities and regional or national priorities. And this might sound a little bit familiar with, especially from the kind of political rhetoric in this country for the past 4 years, are we going to put global interests first, or we're going to put the local or national or regional interests first? It's a little bit outdated idea because when it comes to climate change, it's really hard, to define the borders. And then the other idea that again might sound a little bit outdated is this tension between economic priorities versus environmental priorities. We still hear this rhetoric a lot, especially in the political language, when sometimes there is this assumption that we need to make a choice between the economy and the environment, and it's not necessarily true. So when you would see today some of those examples of scenarios, you would see that there are really 4 major families of stress scenarios. And so those scenarios that start with A1, they all assume that the global development is going to be driven by economic priorities versus over environmental priorities, and also global development over regional or national development, versus A2 would focus on priority for economic development and regional interests, or B1 would be focusing on global priorities and environmental considerations over economic considerations. And finally, B2 would be environmental considerations and regional priorities. So you see, it's obviously, not kind of clearly cut boxes as we see it in the real world, but those are, of course, assumptions for those very general storylines. And then each of these storylines is driven by other models. They're driven by population models, economy, assumptions about our technology and level of technology transfer, the use of energy that we are going to use, fossil fuels versus alternative versus kind of the mixed portfolio, land use models, and agricultural models. For each of those scenarios, then you can actually look at the ways how they work in specific regions of the world. So the world for the stress scenarios is broken into this major regions, such as sort of the super developed countries, such as OECD region, and then RFE region refers to Central European countries and countries of the former Soviet Union. Then you have Asia, then you have ALM, countries of Africa and Latin America. So again, it's a little bit outdated, but it's interesting to look at how this data evolve, and you can actually go to the stress website and look at those specific data in Excel, and you can download them. So you can use them, of course, like if you want to develop an exercise with your student, you can actually look at specific data of what would be, what kind of GDP is modeled, what kind of level of technology transfer would be assumed for different scenarios. So you can do it at a more qualitative level, or you can do it really quantitatively. Another group of scenarios, the so-called RCPs, or representative concentration pathways, were developed by IPCC for its fourth and fifth assessment report. And so the fifth assessment report is what basically we have right now as the latest knowledge on the state of climate change right now. And IPCC right now is working on the sixth report. So it's very likely that most scenarios are going to come in the sixth report. But the logic of the RCP is quite different, and they're all developed by different modeling groups. So different economic models are used in order to provide all this information about population growth and technology transfer and GDP and land use and all those different assumptions that are used in order to calculate possible ranges of increases of greenhouse gas emissions. And then this information is fed into climate models, and climate models then use this information in order to calculate possible changes in the climate system itself. So RCPs are very different, of course, being based on what we assume in those storylines. And really the key difference between the stress scenarios and RCPs is that RCPs, representative concentration pathways, have no fixed set of assumptions related to population growth, economic development, or technology. Those are just kind of very non-judgmental stories about what the world could be. And then based on this story, the model will calculate possible concentrations and then would go from there. So there might be different socioeconomic futures that would be essentially leading to the same radiative forcings in the atmosphere. And so in the exercise today, I will take you through a few different scenarios so that you can actually play around with them and see if it might be useful in the classroom, because then you can see the differences between kind of very benign scenarios such as RCP 2.6, which is very unlikely, unfortunately, very nice and cool scenarios versus RCP 8.5, which is essentially sort of the business as usual scenario where we're heading right now, unless we start drastically cutting our dependence on fossil fuels. So here you see the difference between sort of the good scenario with RCP 2.6, where we are going to see 2 degrees in temperature increase versus 4 degrees temperature increase under 8.6. And you can see that there is that divergence somewhere around 2030, 2040. So we have a little bit of this decision-making time left to build a better world. And then you see fairly drastic diversion between these two modeling scenarios. So I don't want to take too much time on the theory. Those are just background ideas to help us understand the exercises. I do recommend some additional readings. I do recommend to use National Climate Assessment. So this is the first volume of the National Climate Assessment. NCA Volume 1 was produced by 9 different federal agencies in the United States, specifically looking at climate change in the US. And also what is nice, if you are looking at already available lesson plans using the NCA materials, climate generation, which is a part of our MiRCLE diagram, has the entire set of climate lesson plans specifically based on the NCA. And so it's very easy to go back and forth between those lesson plans and this website. And chapter 4 in NCA would also take you through the logic of climate models. Also, there's a wonderful book, Climate Modeling Primer, if you want to take a look at it, that's available as well. And then you have links explaining the stress and RCP scenarios.